Okay, we are live just a little bit early to let people gather, and because I've noticed sometimes that it has to reset your connection if you are waiting there for it to go live. So we'll just hang out for a few minutes before we get started. Uh, while we're hanging out, check out what my wife made me. Let me change my view. So let me there. I think it's really sweet. I'm gonna hang it up this evening, probably. Maybe tomorrow. Probably tomorrow. But yeah. Uh, yeah, we just gonna wait around for a few minutes. Hopefully everybody is checking out their test. I would suggest try to get the transformer test done while we're talking about it. Since you have it, I mean, no reason not to. Uh, then you've got 2 weeks to get the other two tests done. So we'll we'll see what that brings about. Yeah. Uh, we are just about ready to get started. All right, so let's get started. Let's get it started. All right, that should have it on the screen long enough for anybody that's just scrolling through. The reason I draw it every time is so that if you're just scrolling through, you'll see it. All right, so, oh, my holder is over there. Blank is the amount of harmonics on a line compared to the fundamental frequency of 60 hertz. So the chapter this one is in is there is a chapter, I want to say 6, but that feels a little bit too on the nose. Like, how would I remember that? This is lesson 5, and we are in chapter 5. Too easy. So, all of your answers here are going to be in chapter 5. Oh, I didn't finish the button pressing. Oh well. Total harmonic distortion is the amount of harmonics on a line compared to the fundamental frequency of 60 hertz. Uh, let's see. Just to show some pictures of harmonics. A pure sine wave is let's open image in a new tab. Oh, there we go. Alright, so the purple line is your... Wait, no, the red line is your normal wave. That's how it's supposed to look. The purple line is your third harmonic. I've seen this same image, but with a fifth and a seventh harmonic. And what those are is the third harmonic, there's 3 times as many, or has 3 times as much frequency. The fifth has 5 times as much frequency, and the seventh has 7 times as much frequency. And whenever they all go together in a sine wave, or in a system, they create a distorted wave, which makes it, you see how right here This is a pretty good way to see it. Right here, the regular sine wave is hitting its lower peak, while the third harmonic is hitting its upper peak, and that makes it uh, dip like that. And the same, basically the same over here and right over here. It makes really, really weird waveforms, is what it does. And the whole reason that that happens is here is a pretty good. Oh, we do not want to watch that. Don't have that kind of time. Uh, Basically, computer loads. Computers, fluorescent lights, LEDs, they're causing these harmonic distortions and making power loads have lower quality. Uh, Negative sequence harmonics have the opposite phase sequence to the fundamental harmonic. Uh, Phase sequence is it's like 180 degrees out of phase, but it's not it doesn't have the same frequency, just uh, it's negative then positive instead of positive then negative. Uh, Total demand distortion, that is uh, I'm drawing a blank now. I mean, it's the ratio of current harmonics to the maximum current load, but I don't want to just read the answer. Let's see. Yeah, chapter 5 though. This is a lesson that I don't go over much, so I have to reteach myself every year. Current crest factor. Total harmonic distortion? Nope. Odd and even numbered harmonics? No, we haven't. Harmonic sequence. That's the. Most of harmonics, while I look this up, I'm going to keep talking. Mostly what harmonics do is. Okay. What harmonics do is cause more wear and tear on devices in the system, but they don't really. Like, I've never had to do a power quality analysis and look up the harmonics. Uh, they they're important on larger facilities, power distribution systems, like the big power distribution systems. But for like residential, small commercial, light industrial stuff, you're not really going to see much power quality, and it's not a I don't know. It's just not something that comes up around here. Now, if you go up to like uh, data centers in other parts of the country and big computing facilities, then their power quality is going to be questionable, and you're going to have to pay attention to that. We just don't have the types of facilities that need it so much around here. I'm sure there are facilities around here that need it. It just doesn't come up that often, which is why I haven't had a chance to see it. Uh, the total demand distortion is different from the total. So I'm looking at page 103 for this information, and total demand distortion and total harmonic distortion are different. Uh, the total harmonic distortion is taken from the power, like the feeds, and total demand distortion is taken basically at the load. It takes into account the maximum load current, so it would take into account like a motor's amperage rating in the figures that it does. A blank is a voltage or current at a frequency that is an integer multiple of the fundamental frequency. A harmonic. So this is back to the beginning. These are harmonics are what are other frequencies in the same current that are at different frequencies. They're so if you have 60 hertz, a triplet harmonic would be what 60, 180 hertz, but it would be happening at the same time in the same wire. Only single phase loads generate triplet harmonics. So a triplet harmonic is that 3 times harmonic. It's triplet harmonics cause things like overloading of the neutral, because if you think back to that picture, this one right here, the triplet harmonic, the single phase load has another, like, you'll have another phase that's going 180 degrees out of phase with it. And if you are sharing a neutral with that, you won't be completely canceling each other out on the neutral. You will be mostly or only partially canceling each other out, and that will cause problems. That's not the right button. We're over here. Okay. A switched mode power supply is useful for canceling out harmonics. So once you figure out why harmonics are bad, then you're going to be, well, how do we fix it? There are transformers, special power supplies, and various other pieces of equipment that will cancel out these harmonics. And then current crest factor is the peak value of a waveform divided by the RMS value of the waveform. So this is not necessarily only to do with harmonics. It is whenever we were like AC systems, I think was the lesson at the very beginning of AC theory. We multiplied or divided the peak voltage by 0.707 to get the RMS voltage. I think it's times 0.707. The crest that 0.707, actually it's the opposite of 0.707, 1.414. That's the reciprocal. Gives you that's what the crest factor is. We just didn't put a name to it back then. But yes, page 106 is where you'll read more about that. Page 106. All right. That finishes that one. We got a couple minutes. Let's give... I have a couple people that do it at the very last second, so I'm going to give them a moment. I'm going to end the stream here, though, and at 4 o'clock, I'm going to put up the next one, and then at 5 o'clock, I will be back to go over the last lesson.